In the last video, we did a survey of forces, developed an intuitive definition, which we'll expand later. And we realized that we could break them into long range and contact forces, and kind of broke apart at least some of the contact forces. Okay, so in thinking about how a force affects an object, one of the toughest things to do sometimes is just plain to figure out what are all the forces acting on the object. So to that end, we have a thing called a force identification diagram. And it's probably just easiest to show by example how one of these would work. So what I'm imagining is that you are skiing on one of those basically reclaimed landfills that's now euphemistically billed as a mountain or something like that. And when you're at one of those places, you can grab a tow cable to go up said quote unquote mountain, so that you can then go and take another run down the hill, if you can even call it a hill, but you know what I mean. So when we look at something like this, we can think about how it's moving. Sometimes that's helpful. So, but a velocity is not a force. I'm just throwing that in there. So to figure out the forces that would be acting on you, if we need to think about this as we build our force identification diagram here. Turns out that what you do is, after you've drawn a picture of the system you want to study, and its surroundings, first thing you do is you just draw a circle around the system you want to study, in this case the skier. And define contact forces, it turns out that you can just look at where the circle intersects. So here it intersects with the tow cable, so that's going to be a force of tension. And it also intersects with the artificial snowpack. And so those will be, so we'll have a normal force from there, because otherwise you just fall through the snow if the snow weren't pushing back. And because you're moving up the hill, so okay, that velocity vector was useful. That means you're sliding against the surface, so that means there's also a force of kinetic friction. So we can look and identify our forces. So we have a contact forces of tension, normal force, and kinetic friction. And I'm using reasonably standard notation here for these. After you've worked your way around the circle, and you've identified all the contact forces, you then have to ask yourself, are there any long-range forces? In this case, the answer is yes, there is. There is gravity. Now, I know that a lot of books prefer to call it weight and give it the symbol W. I am not a fan. I will have a rant in a later video about why not to call it weight, but for now, just suffice it to say that in the physics community, weight does not have a well-defined term. And usually when you say weight, you often, but not always, mean one of either the normal force or gravity. So since those are unambiguously agreed upon, I always take the attitude that you should just call it what it is. But more on that later. All right, so once we've identified all of our forces, the next step is to think about how the forces will act on the system is to draw what's called a free body diagram. Now, I've already alluded earlier, but it's worth doing again here. In a much more advanced treatment, advanced undergraduate treatment, you can show that if an object is rigid, you can completely describe its motion as the translation of its center of mass combined with the rotation of the object about its center of mass. So what I've done here is I've just plain drawn a dot, and this dot represents the center of mass. So just like in our motion diagrams, this is the center of mass. And since we can, for all purposes, treat the object as if it were a dot at its center of mass, we can go ahead and attach our force vectors there. So, sure. So for instance here, this would be our tension. And notice here I'm making it line up with the string, and I know it's going up. Why? Well, first off, if I cut the string, then we know that we're going to go sliding down, right? So it must be that it's pulling up. But also, we know that up at the top of the landfill, I mean mountain, there will be basically a giant pulley that's being turned by a motor. And so that pulley combined with U is serving to stretch the cable. And since the cable's getting stretched, it wants to return back to its original length. And so doing, I'd have to pull U up the hill to make that happen. All right, let's think about the normal force. Normal, remember, means perpendicular to a surface. So I'm drawing it perpendicular to the snowpack and labeling it. Friction will be parallel to the surface, and it opposes the motion. So again, since we noted that the velocity is up the hill, the force of friction has to be straight down the hill. And then, so, okay, we've gone through all of our contact forces. We're just left with gravity. And we know that gravity is going to act straight down. Like so. And that's a free body diagram. So when you're thinking about what forces are acting on something, step 1, force identification diagram. Step 2, free body diagram. Now, in the next video series, we will be looking at Newton's laws of motion. And in order to apply Newton's second law of motion, we'll have to calculate a thing called the net force acting on an object. So net here means what you get as the result of a vector addition. So as an example here, let's imagine that you have 2 tugboats that are pulling some big ship into harbor. Like so. All right. Well, if our system is the ship, what forces do we have acting? Well, acting straight into the screen would be gravity. Acting straight out would be the buoyant force, which is a contact force that we didn't get into. It's one due to fluids trying to make things float. And we cut through the 2 strings here. So in the plane of the screen, our 2 forces are going to be the 2 forces of tension from the two cables from the tugboats. So we'll just draw them in. So there's one force of tension, and let's see, we need to point the other one with the cable. Let's say it's not pulling as hard on the ship for whatever reason. Okay. So then to get the net force, what we do is we just add them up. So here, good as anything would be to use the parallelogram rule. It's often the case when you're doing forces, because with free body diagram, we put all the tails at the dot. It's often pretty straightforward to just add up with the parallelogram rule. So we will finish off the parallelogram, something like that. So then the net force will point like that. So this isn't a different force. This is just the vector sum of the forces that were acting on the ship. Now what we will see is that forces obey a thing called superposition. It's just a fancy way of saying that the combined influence of two forces is the same difference as if we got rid of both of those forces and created a new force, like say had a super duper tugboat or something like that, that exerted the net force. So even though the net force isn't an actual real force of nature or anything like that, it turns out that the combined influence of these two is just simply the sum of the two. Nature doesn't have to work that way. It's an open but we are very, very glad that it does. Alrighty, so in the next series of videos, we will be taking a look at Newton's laws of motion and using and analyzing forces to start to figure out how things move. Catch you in the next one.